Well, we've concluded a study of matter. We've looked at writing formulas for compounds, writing equations, looking at molecular shapes as we do our Lewis dot structures for covalently bonded compounds. And now we start a new book in chemistry. We're going to be looking at phases of matter. You know, matter can exist in three main phases: solids, liquids, and gases. And if we want to describe phases, we can use something called the kinetic theory as we talk about matter in these different phases. There are a number of points about the kinetic theory that you should know. Number one, this might come as a surprise to you, but all matter is made up of atoms or some smaller particle. All matter is made up of atoms. It doesn't matter if it's a solid, a liquid, or a gas. What's the difference in these particles? Think about it. And take water as a good example. You're thinking a bent molecule, bond angle maybe about 105. It's very polar. But water can occur in different phases. If we have water molecules very close together, then we have solids. If we have water molecules farther apart, the liquid phase. Even farther apart, in the gas phase, water vapor. Vapor is a term that you use for liquids that are found in the gas phase, but normally they're liquids. So when you're looking at the kinetic theory, it says that all matter is made up of particles. You should understand that the difference then in the matter is the space between the particles. How much space that you have between the particles is what's going to make a difference in what phase the substance is going to exist. The second point to the kinetic theory says that these particles are in constant, rapid, straight line motion. Let me show you. When you look at this diagram here on the board, I have an Erlenmeyer flask, and let's put a particle of a gas in here. This particle is moving in constant, rapid, straight line motion. And it's not going to change its direction unless something gets in its path. So let's say it's moving like this, but it is going to hit the side of the container. And when it hits the side of the container, it is going to change its direction. Hits again. And these hits of this moving particle creates a force. This force is called pressure. It's going to be one of our major topics in this video, looking at pressure. So pressure is a condition that is established with matter. And these particles all have energy, and so they're going to hit on the sides of the container and create this force. The third point to the kinetic theory is that when you hit the side of the container, there's going to be a collision, and all collisions are elastic. I'm not really sure how I can explain an elastic collision to you, but I can explain something that is not elastic, and you'll understand it. For example, if I were going to take a basketball and I were holding it here and I were to let it go, you know what's going to happen. It's going to fall and hit the ground, and it's going to come back up. But where will the next rise of the basketball be? Will it come back into my hands where I released the ball initially? No. You know that every time the ball bounces, it's going to be coming back up to a lower and lower position. What would you think if the basketball constantly hit the ground and came right back up to the point of release? That's an elastic collision. An elastic collision says that there is no energy lost to friction, to heat, to some other form of energy. Kinetic energy stays kinetic energy. The fourth point to the kinetic theory says that there is no attraction or repulsion between particles. Tell you what I want you to do right now. In your notes, I want you to mark the fact that points 3 and 4 both apply only to ideal gases. We'll be talking about the difference between real gases, like what I'm breathing, and an ideal gas. And then the 5th point is simply an equation that you know. Ke is equal to 1/2 mv squared. You know that the kinetic energy is related to the mass and the velocity of this particle. Did I say that right? I hope so. Anyway, what I need you to take into consideration is that when we're looking at particles, not all the particles are going to be moving with the same speed. There will be an average speed of your sample of gas particles. The average speed is the temperature. Temperature is a measure of the average kinetic energy of your particles. So, as we start to look at gases, and really all phases of matter, what we see is that what's happening with these particles will depend on the conditions. The first condition that we might want to look at is what was brought up here, that we create a force known as pressure. Pressure can be defined as force per unit area. Now, when I think of pressure, I can think of 2 different types of pressure. First would be the pressure of the atmosphere around me. You know, you can listen to the weather report in the morning and they'll tell you the barometric pressure. A barometer is a device that is going to read atmospheric pressure. Now, is the pressure always going to be the same? Of course not. I think you would understand that if you look at a mountain range, let's say that you live at the foot of the mountains, maybe somewhere like Atlanta, which is at a low elevation. You know, here we have a lot of gas particles, and a lot of particles are hitting against my body, creating a force known as pressure. The average pressure in Atlanta is probably less than the pressure if you lived in Denver. You know, when you're that high, at that high of an altitude, there are fewer particles. And you know this is true because you know that if you keep going higher and higher, up, up, up into the sky, think about airplanes, at some point there's very few particles. And you would have to be in a pressurized cabin in an airplane because there's fewer and fewer particles of air, oxygen and nitrogen, for you to breathe. Well, the fewer number of gas particles you have, the lower the pressure. So the highest pressure that you're going to have is going to be at sea level. At sea level is going to be the highest pressures that we would be recording, you know, above sea level. And so we set this as sort of our reference point, and there is an average pressure at sea level. That's atmospheric pressure, read by a barometer. And so when we want to record pressures, that the pressure can be recorded in different units. And there are different units that you will be working in. So let's take into consideration that if we're talking about sea level pressures, okay, pressure at sea level, this is called standard pressure. Standard pressure. The standard pressure is the pressure at sea level. And this might vary a little bit from one location to another. You could look at Hawaii, the shores in Hawaii, then you could go to Australia, you could look at the White Cliffs of Dover, and you could look at the fact that the Statue of Liberty sits in the ocean. All these places are going to be at sea level, and they're not going to all have the same pressure. But the average pressure exerted at sea level is said to be standard pressure. The units for pressure can be in units of atmospheres. 1 atmosphere is standard pressure. But maybe you don't want to measure in atmospheres. Maybe the information you're being given is given to you in millimeters of mercury. It is 760 millimeters of mercury for standard pressure. There was an Italian physicist back in the 1500s, Torricelli. He did a lot of work with pressure, and so this is also 760 torr, after the Italian physicist. Now, you can see that these two are exactly the same as far as the number. But other units that you should know would include 101.3 kilopascals. Kilopascals is the SI unit for pressure. And then just to give you some idea of what we might be talking about, if you want to look at something we will never use, 14.7 PSI. PSI stands for pounds per square inch. So these are all standard units of pressure. We'll be working in a couple of these units. So you need to know that these are all equivalent. 1 atmosphere is the same as 760 millimeters of mercury, which is the same as 101.3 kilopascals. Now, what happens if you change the pressure on a certain volume of gas? We're actually going to stop and take some data. And what I have over here to the side is a pipette that has been filled with some blue food coloring. So let's move there now. All right, we're going to take the data, and what we see here is that our first data point, which is for the volume of gas with no pressure on it, it looks right now that this volume is about 9.5 centimeters. With zero pressure, 9.5 centimeters. Now, what I'm going to do is take one of your chemistry books, and I'm going to place this book down on the bulb holding the liquid. What do you think is going to happen to this little piece of gas, of liquid here? Well, as I squeeze and put pressure here, whoa, I've got a leak. So let's see if I can get this to go back and get this to close. Because if not, I'm going to have to start this experiment all over. Let's see if I can get this to close down really tight so that it's sealed. Okay, we'll try this one more time. Okay, my starting is a little different, but I'm going to just give it a try here to see if it holds the pressure. Because if it keeps leaking out, I have to start all over. 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 Just stop it. Okay. All right. So what we have here is a thin stem Boyles pipette. The stem is of a fairly consistent bore, opening size. And in the far end we have some blue food coloring. We're not interested in the blue liquid. What we're interested in is the gas volume. And so I'm going to take some readings. Pretty rough, I'll grant you, but it'll be fast. I'm going to look and say that the volume of the liquid is equal or related to the length of the gas in the tube. So my first reading is going to be that with no pressure whatsoever, I have a volume of about 9.5 centimeters. Now I'm going to very gently place a textbook on the stem of the Boyles, on the bulb of the Boyles pipette. Look at what's happening. As I increase the pressure, the volume of the gas changes. increasing the pressure by adding a book is going to cause the volume of the gas to decrease. Now let me take this measurement, and I'm going to have to just adjust that, and I'm going to say that the volume here is about 7.9 centimeters. And then I'll add a second book, which is going to decrease the volume to about 6.7. And then a third book, cutting the volume down to about 5.7 centimeters. And then a fourth book, which is going to take the volume down to about 4.9 centimeters. Okay, let's look at this data and see what it tells us. But just from the experiment, you can see that increasing the book pressure decreases the volume of a gas, an inverse relationship between pressure and volume. All right, let's look at our calculator screen now, where I've entered into L1 the number of books exerting pressure, and into L2 the length of the stem being occupied by a gas. You can see that as the books increase in L1, the volume of the gas decreases. Let's take and look at this data graphically. So, if I go and turn on a plot of L1 and L2 and look at the data, you see the data points, they do not look linear. And we always like to see a linear relationship. So I'm going to go into the stats, and I'm going to do a third column where I'm going to label, let L3 equal L2. Actually, I'm going to change that. Let it equal 1 divided by L2. Let's look at the inverse. And when we look at this graph, I'm going to go in now and simply turn on a plot where I'm going to be graphing L1 versus L3. And when we see this graph, this looks hopefully a little more linear. Remember how quickly and what a crude experiment I was performing. You could do a linear regression on these data points and see that this is going to be a closer to a straight line, especially if you take the time to take good measurements. So let's look at the board now and see what this tells me. This is what I see. I see that there is an inverse relationship between pressure and volume. That is, the pressure increases, the volume decreases. But what is so amazing is that if you look at this, if you take the pressure and multiply it by the volume, you will get a constant value, K. Now, I took my first measurement. We'll call this P1 and V1. It gives me a constant value. When I took my second measurement, which would be another P, P2, V2, I would get the same value of K. It is a constant. If this is true, then substituting for K, I would come up with P1, V1 is equal to P2, V2. This is Boyles' law. Pressure and volume are inversely related. When we know any three of these measurements, we can solve for the fourth. Volume and pressure can be in any units, but you need to be consistent. So if you're in pressure of atmospheres, you have to stay in atmospheres. If your volume is in milliliters, you stay in milliliters. But as long as your volume is consistent, you're going to be getting correct answers for solving for your unknown. Boyles' law, an inverse relationship describing pressure and volume relationships to gases.